Good morning. Hang on.
Hi.
Now I can hear you. Hi.
Hi, good morning.
Good morning.
Let's get rid of these.
Yeah, I will get rid of my background. How do I do this?
Good morning.
Hello.
Hi.
Right. Well, it's a small group today. What's going on? Did I forget a public holiday or something?
Not that I know of.
I know what it is. I didn't put a reminder out. Well, welcome to Neuroccino. This is oh nice, the first paper's coming through. This is the classical group, I should say. You know the drill. Present a paper. I think we have 2 today, if I'm not mistaken. Yes.
Yeah, but it's more science news than a true paper that I can go delve on and everything.
Guys, the rule of the game is bring science that excites you. You don't have to justify or
I know. It's just that
apologize for your papers.
I can't stretch the time that I will present on too long because I can't just.
But the idea is to keep it short and sweet anyways.
That I can do.
And there's another person in the crowd today that I know doesn't feel 100% about the paper because it's an opinion piece rather than a scientific paper. But yeah, the whole idea is you take a piece of science that got you excited for whatever reason, and you tell us why without having to worry about what you're bringing in the first place, okay?
Sure.
There's no wrong papers, just like there's no wrong questions. We got 3 papers I can see now, so we better crack on. I know you sometimes ask me for order. No one has done so today, so random. Laura, do you want to start?
Okay, yeah, give me 1 second.
Sure, floor's all yours.
Just correction, it's a wrong link that I sent. This one is better.
Cool, thank you.
Okay, so as Stephanie said, this is an opinion piece that I read last week and that I think tackles some interesting issue that we have in science in general. So we cannot do any type of research in humans, and therefore we use other techniques in animals. The problem is that when we do this, we have an explanatory gap that is given by the fact that with non-invasive techniques in humans, we achieve one type of information that is at the macrostructural level. But then when we do research in animals, we can investigate phenomena at the microstructural level. But sometimes when we do this, we neglect what is going on in the rest of the brain. So what is something that is really needed is that we try to put together this information, although it's come from different species. Something that the authors propose, first of all, something that the authors propose is that we can use 3 different approaches that can allow us to do this cross-species analysis. But first of all, we need to consider the fact that although we have different brains in different species, there are some features which are preserved. For example, we have preservation of the structure and the function of the neural circuits and the encoded sequences within the human genome and in other mammals. For example, we have this 99% overlap between human and mouse. And this is also true for some patterns of gene expression, and we have a 79% overlap between humans and mice. So what the authors propose is that we use these 3 approaches, which are complementary, in order to put together the information that we get from different species. The first approach is that we should use different tools, but within the same species. For example, as we see here in mice, we can use functional MRI, And then we can also use electrophysiology. This is very important because it would allow us to compare the information coming from two different techniques. For example, we could try to relate the bold signal from fMRI to what is going on at the neuronal level. Then the second approach consists in using the same tools across different species. This is a direct investigation of what's going on while doing a task in the two species in terms of activity. The problem is that we have different brains, so we should try to create a common space with the use, for example, of landmarks, which can allow us to put together the information coming from the two species, but in one same modality. And then the third approach that they propose is that we use the best techniques available in each species. For example, MRI in humans, and then electrophysiology in mice. And let's say that there are some measures of the brain functioning that can be compared between the two modalities that we have. For example, previous studies said that we have these oscillatory dynamics that are recorded with MEG and that can be possibly and directly related to invasive measure of the local field potential. But another discourse is that it's more challenging to try to relate non-invasive measurements that we have in humans to the real spiking activity or synaptic processes that we have recorded with electrophysiology. Something that they propose is that we should, for the structural part, using some standardized templates in order to put together the information. And then we should find an analytical framework which can be common for the data that we have. Something that has been done in the past was to use the representational similarity analysis to analyze data coming from different species and from different techniques. So as you see here, we have the same type of stimuli which are presented to the two species in humans, which are doing an fMRI task, and then in mice during electrophysiology. They created these representational dissimilarity matrices, and then in this way we can try to understand which is the way in which the information is represented in the brain in the two species, in this case in the inferior temporal cortex. And therefore we can see whether there are some similarity in the way in which the information is represented in humans and in monkeys. Another thing that they say could help us to put together and analyze information coming from the different species and different technology is possibly computational modeling. They do this example of this algorithm that is called temporal difference learning, which is based on reinforcement learning algorithms. And basically, it says that the prediction error signal is a good approximation for the temporal profile of activity in midbrain dopamine neurons, recording using electrophysiology. But let's say this is not the rule. So it's difficult to find an algorithm which is able to explain both the macrostructural and the microstructural level of activity. And let's say I found this paper interesting, this opinion piece interesting, because it's a call for an effort towards, let's say, filling this gap that we have between species. And I think it's very important. For example, in my experience, when I'm looking for stuff regarding connections, sometimes I read about tracing studies and I say, okay, this is awesome. But then when we come to putting together information and trying to understand what we can do about that piece of information coming from animals in respect to humans. It's a bit tricky. And so, yeah, I don't know if you have an opinion on this. I won't be able to answer your question because I'm not an expert, but yeah.
Thank you, Laura. Very interesting paper. Any questions? No? Well, let's see if we can have a little discussion about this one, because it's quite interesting, I think. And there's really two, if not more, problems here. And one is the methods. Can we actually apply the same tasks across species? And can we expect the same behavior or neuronal activation patterns from the same task? And then the other, not problem, issue, whatever, point of consideration is what species is the best one to study? As in, can we assume that a mouse is close enough to a human for certain things, but not all things? Which monkey model is the best monkey model? Should we even use monkeys? Like, this is a huge bubble. Well, and then actually the third is, how do we bring all these different type of methods together? So there's more and more push for multi-modal imaging and getting the best of each method and then try to combine it. But that in itself is difficult enough, as a couple of you know firsthand in this audience. But then trying to bridge that between species certainly does not make it easier. I see a lot of nodding and smiling. Any comments, any opinions?
So for me, for what concerns the tasks, like trying to do the same tasks in different species, in this paper, this work, they also say that you can use, for example, virtual reality in order to do these spatial navigation tasks, and then try to understand whether these tasks leads to activation of something. They also do the example of place cells, which is something that has been described in different species. And then one other thing I wanted to say is that something that I really agree on for this work is that eventually what they call for is for a cross-validation of technologies to solve this problem. So, for example, if we can have tractography in mice, and then we can also have tracing studies there, and we have a real validation of the technique, and we can translate this to human without doing, of course, tracing studies, but we can understand the validity of the technique that we are using.
To a certain degree. It's a different anatomy.
Yeah, sure.
Yes, if I can say, like when Laura was speaking, I was thinking, why we are not doing this? This makes so sense, but maybe there are all the problems that Stephanie talked about. But probably we can do more effort, as Laura was explaining. There are maybe some way to merge this data. So yes, it was interesting. And yes, my question when Laura was explaining is why we are not doing that. But probably there are problems, I think. I never.
Well, I remind you of a brain hack project that we did a while ago, where we tried to combine all the different modalities, and you know how difficult that was.
Yes, but at least like for the MRI, make something like the most comparable as possible between animals and humans. That is something that can we achieve with all the limits of the techniques, of course, that we can have.
Thing is,
maybe
with MRI, there is a big component, I think, with the human, that is the comprehension of what's happening, that you cannot have with animals. Animals, you can only, at best, make them used to the machine, the noise of the machine, and the restraints that you have to put them in. But it is inherently very different from how a human will perceive the whole thing. So I think, I mean, for a very specific task, it might be ignored, but I think it's a very big caveat on this kind of translational stuff with the MRI. Maybe it's not, but I doubt it.
Ma'am, I just want to ask this. It also depends on the kind of question you are asking, right? Because if you are focusing on the visual areas, for example, where they investigated initially in cat brain, the uh, uh, synchronization of patterns of firing of neurons in a specific area of P1, which could be also translated to human beings, correct? So it really depends on what kind of questions you're asking and the similarities between the animal investigation and the brain of that particular species and humans, right? Not really. I mean, we are thinking about advanced level uh, processing in the brain, then certainly the kind of question, the comparison would be difficult. But processing such as visual and auditory or uh, uh, similar kind of investigations, maybe.
I think that are automatically processed by the brain, you mean, and that doesn't require a specific state
high
of
level
mind
of processing. That's correct. So it depends on what kind of question we could ask and translate it across species, right?
Sure.
The other thing to consider is that an MRI scanner is far from a natural environment. And while it's easy to get, well, within reason, relatively easy to get humans into an MRI scanner, if you want to do similar tasks with any kind of animal, then it's a matter of training. And you might be looking at years of training here, which certainly doesn't make it easier. And again, slightly less comparable. Wow, thanks for the discussion. There's no further comments, not that I can see. Let's move on to the next paper. Victor.
All right. Let me share my screen. Okay, so it's a piece of news, science news, that I've seen quite a bit in different science alert and everything this last week. It's not actually such a big deal, but it's quite interesting if you are into, like me, if you are into space stuff and astrophysics and the like. So this is about axions. So just to introduce a bit of the principle, there are some problems with the model of how particles, subatomic particle work, that have different solutions, and one of them is the existence of a theoretical particle that we haven't detected yet, that solves a lot of those problems, and it's called an axion. And the thing is, it's also one of the candidates for dark matter. I don't know if any of you are familiar with dark matter. It's all right. So just to recap for those who would not be at least on YouTube or anything, it's when the astronomers look at the sky and how the objects in the sky, like stars and galaxies and clusters of galaxies, how they behave, they see that there is a lot of mass missing. Like they see a gravitational pull of something that they cannot see and that they cannot explain only with the normal matter than they usually look at. Normal matter is everything that is composed of proton and neutron, electrons, like what we call matter, usually. And since they can't explain it with this matter, they they say that there has to be another kind of matter that we don't know of, that does not interact much with the normal matter, so we can't see it. So they dubbed it dark matter because we can't see it. So basically, and so these axions that are the that is a solution for another physics problem, can fill the gap, because they would very weakly interact with matter, and there would be a lot of them, so it would work. So this is the basics of where we were. And there was recently, the thing is with axions is that they can, if they exist, they would be produced by neutrons smashing into each other. And they have a very special property, is that if they are under a very strong magnetic, in a very strong magnetic field, they can transform directly into photons, like X-rays photons. So this is something that is one way to find these axions would be to have a very strong magnetic field and look at inside, if you see like photons like popping up from seemingly nowhere. So there are experiments that are trying to do that on Earth, but with the kind of instrument we have, either they do not exist or they are not sensitive enough. So for now, nothing has been detected. But this paper argues about another source of those X-rays that that might be due to axions. So it's focusing on the on two neutron stars that are relatively close by from an astronomical point of view, and that are studied by astronomers. And those two neutron stars, so because they are mostly made of neutron, they can, just with the normal heat inside of them, there will be a creation of, well, if there are axions, there will be creation of axions inside of the neutron stars, and a lot of them. And also neutron stars have this extremely powerful magnetic field. So when you get the two together, you say, okay, it's perfect. It's like the perfect way we can detect axions, because it creates a lot of them, and it has a magnetic field that would transform them into light. And so in theory, there should be more X-rays coming from neutron stars than what we expect from our models. And this is exactly what these two neutron stars that are being looked at have. They have an excess of hard X-rays that is not, that the astrophysicist cannot explain by any of the known mechanism to produce X-rays. So this is quite exciting, but this might be a clue that indicates that axions do exist, and that would be great news. So this is what the paper is about. But this is not at all like a proof, because we are just saying, okay, there are X-rays coming from the stars, and we don't know why they are here. And that would, it would go in the right direction for this exotic theory, but actually we have no idea what's happening there. So we have to stay cautious about this kind of results. But yeah, I mean, it's this kind of thing that you'll find in science reports and stuff like that, that are like, oh, we've got a new particle. Probably not. It's like aliens, but it's not aliens. It's but maybe, who knows? And yeah, to me, that is a bit of a space nerd. It's pretty exciting. So yeah, that's it.
Thank you, Victor. Funny you mentioned the aliens, because the way you described it, I had like aliens in my head as well.
Yeah, completely.
But I can see you definitely put your physics hat on this morning. And I know the next paper is going along the same direction.
Incredible.
It's an interesting morning. It's like definitely out of our comfort zone. Now, I'm not a physicist by any stretch of the imagination. But when you said that you could test for it with a strong magnet, how strong does the magnet have to be? I'm assuming an MRI scanners aren't strong enough.
No, I don't remember exactly the value, but it has to be very strong, probably over 10 Tesla or something. I don't remember the value. The thing is, you don't need to have like, well, the problem is they don't know exactly what will the mass be of these actions, and depending of their mass, you might need a stronger magnetic field than what we have on Earth, that we can create. So the experience that they made for now on Earth is like they have like neutrons in a room that they smash together, a big wall that prevents anything from going through it, and at the other side, like a tube, inside they create a strong magnetic field, and at the end of the tube, a detector of X-rays, an X-ray detector. So in theory, like you smash neutrons at some point, they go through the wall, and they are the only thing that can go through the wall because they don't interact much with matter. And then they enter the magnetic field, transform into light, and are detected. And with the magnetic field that they tested right now, it didn't work. Like nothing happened. So they are like, so it cannot be up to this mass of the particles cannot be up to this mass. It has to be a lower mass. But it's like, it's just, we still haven't detected anything with kind of thing. So I guess we don't have the magnetic field machine strong enough right now.
You certainly look very excited about this.
Yeah, I love that.
Patrick, you unmuted. I'm guessing that's for a reason.
Yeah, I don't have any idea about physics either. So I'm just, my questions might be like coming from a very naive standpoint, or will be coming from that.
Sure.
So when basically, I mean, I see the logic in just coming up basically with unobserved feature or particle or whatsoever that solves the problems that we can't solve with the set of known particles or set of known features in general now.
Yeah.
But there must be certain rules applied to define such particles, right?
Yeah.
Because I can imagine, like, for instance, it needs to have a mass, obviously. Probably not detectable, but it needs to have one. We cannot just go with, or how is that?
Not necessarily. Actually,
Okay.
it's way above my head too. But how the physics work is that they have a problem and it's translated into pure mathematics, and they solve the equations, and so they have usually a lot of different possible candidates that could explain possible solution that could explain the what they see. And some are like, yeah, you have to have time reversal and stuff like that, so they just like out of the door. And then there are several that are competing, and some have particles without mass. And sometimes you say, okay, if it doesn't have mass, so it cannot have, it has to have this kind and this kind and this kind of properties. And then you test for those properties. And it happens that sometimes you can rule out this solution, and it's what's happening usually in this kind of physics. It's you rule out more and more solutions of your equations until you have something very specific that you can test. And say, okay, we have the Higgs bosons. It's detected. It has to be the Higgs bosons, and you can say in the CERN at CERN they detected it and everything, and they know it's here. But for example, for some time the the neutrino, that is another very not that much known particle, but the neutrino was expected not to have mass, and in the end we found that it could change during its flight from one place to another, and to be able to change means that it has to have a mass for some reason, and so we had to come back to this, and they had to recompute everything, and so that's it's usually like solutions to mathematical equations, and then you just try to reduce by testing, reduce the different solution until you have one that is the only one possible, and you can test it in like a particle accelerator and say, okay, this is it.
Okay, cool. The reason I'm asking is because basically you need, in order to test it, you need to have at least some idea, right? What to expect. Otherwise, you don't know when your test will be significant, or when your test will actually give you the proof that a certain particle you expect exists, right? So I'm wondering to what extent then all these hypotheses, or generally speaking, hypotheses may be biased by our expectations here. Similar as they can be in neuroscience, for that matter, where we can only, or we tend as humans we tend to group observations by the categories and knowledge that we already have, right? So if I don't know how or I expect that a unicorn particle exists, I expect it to have a horn, for instance, right? Because that's kind of my definition of what a unicorn particle would look like. So in that respect,
I want to see that now, Patrick.
Well, it's not yet tested. I'm putting it out there.
I have a unicorn on my passport. I think I know the country. You need to start looking for it.
but you know what I mean, right?
Yeah, and the thing is, well, let me finish. Yeah.
No, please,
okay.
Go ahead.
The thing is, you're exactly right. We can test, or well, to know if a particle exists, we'll have to test and to have like definite answer for this. But how do we find candidates? You are saying like the way you find candidates is biased, obviously, and it is completely. This is also why there are so many different theories about so many different particles that could explain, for example, dark matter, or the string theories and everything. It's something that is really not. It's usually people they are playing with the math that are underlying the whole problem, and they find a solution that they find beautiful or elegant, and they say this must be it. So yeah,
because it's so beautiful and elegant that it would solve, and hence it has to be that. I don't want to bash now on physicists or anything, because I think it's amazing what they're doing. But I'm just wondering, like, how does it work? And it's just interesting to hear about it.
Yeah. Sure.
If I can say something, like
against you now, Patrick.
No. It's like perfect what you said, as Victor explained. Also, I wanted to ask if this can be simulated, and you already explained that. So this really makes sense. I just want to say that it's sometimes like what we say, like playing with mass or elegance is looking for a symmetry. So usually what I understood, because I'm not an expert in this, but what physicists do is, so you have to have like a balance between things. This is why like mass can transform in energy, and why you are looking about these particles that you're not sure that exist, but you are supposing that they exist because you need to have a balance, because we have a principle at the beginning of everything that you have to conserve energy. So so you have to transform in something if this energy suddenly disappears. This is why we are thinking that the dark matter exists, because you have something that if you say 2 plus 2 is 3 plus 1, and if you can see this one, you have to suppose what this one can be. They can be like a neutrons, an axon, you don't know, and you simulate all these scattering things because you want to find this solution. So it's not that they are like invent, like, yeah, of course, with the math you have to trying to find a solution. So everything is behind the symmetries, I think, and so I don't know if this can ask some of the question, but I think this is the principle, yeah. And if I can say, like, I really like that in the article that Victor explained, you have some hard X-ray as something that came up in this process, and maybe this can have applications in the medical field. Let's think when you want to treat a tumor, you have accelerators of carbon protons or because you need like a lot of energy. I don't know if we can see, I'm asking to you, Victor, if we can see some application of this, or we are far behind from this.
Yeah, I don't know. I don't think there will be application of this exactly, to be honest, because it's already extremely hard even to produce those this way, and we have way easier way to produce X-rays. But yeah, I guess.
Okay. Yeah, maybe like colliding neutrons.
For now, yeah, actions, we don't even know if they exist. So let's not get excited too much about it.
Okay.
What I was thinking is, if it's mathematically beautiful, or if it's it's certainly a model, right? One of the models, theoretical model. If it's mathematically beautiful, it doesn't really imply that it has to be true, correct?
It's true.
I certainly respect physics and the work the physicists are doing. It's one of the best sciences we have, and in terms of accuracy, we have gained a lot, and we have understood nature much more in terms of physical sciences. And I'm sure, like how we said that maybe Higgs doesn't exist, and we now know that it does, but it doesn't really say that, okay, if we presume or reach to a particular conclusion that a particular a particle exists, it has to exist. It is not necessary, right? What I'm also trying to relate it to is our understanding of consciousness, and how far, like we certainly are very good in predicting particles and trying to find out the particles, although they are so difficult to really derive mathematically and formulate a theory behind it. But we are how far are we in terms of really understanding the problem of consciousness? And because we do have so many theories about it, right? Which try to explain, okay, it is interaction, and many different ways has been predicted, but we really don't know what it is. So how far is physics? I mean, how far is neuroscience in terms of predicting what consciousness can be, and in comparison to what physics is doing right now, that is predicting the laws of nature? I think they are pretty close, but we are still, although it's there with us, and we are thinking at every point of time and investigating. There are millions of people who are investigating, but still we don't know much about consciousness. So I just was trying to relate it to
I see.
our field here. So how far are we
I think,
compared to physics?
Yeah, I think it's hard to really compare because on the one hand, on the study of consciousness, it's more like we have a problem of even of definition, exactly what is consciousness. Here in physics, it's more like I see your point actually. It's like we have something that we can see, and we don't know how to explain it. And yeah, I see.
I just like this example. I really like it because the thing is that that typically when we're talking about psychology or neuroscience, and we're talking about it with like biologists or physicists, they used to give us this label of not being a hard natural science, right? Whereas, well, yeah, we still need to define to some extent our axioms on which neuroscience is based on or psychology is based on. But, well, at least we're not there that we come up with things just to prove our theories. Sorry for that.
I mean, they come up with a lot of stuff, but then they have to prove they are right. And that's the hard part. In psychology,
we have a couple of unicorns in psychology as well.
Oh yeah. Yeah, true.
Lovely discussion. I hate to interrupt you at this point, but we have one more paper.
Sure.
That falls into a similar category in terms of physics and theory. So Leah, if you're ready, take it away.
Yes, so can you see my screen?
Yes.
Okay. So also this is a paper published like 3 days ago in Nature Physics. So is about a physics background, but what I always want to do is trying to find an application of all these knowledge or mathematical tricks, formulations that we have in physics. I'm really interested in the translation to something that can really be useful. For example, imaging applications, and this is like a little bit of my story, but also in this paper, they are trying to do that. So it's called maximum information states for current scattering measurements. So they are trying to simulate and formulate what is happening in a scattering process, and they used a new tool that is the maximum information states. And I really love the introduction because they're trying to do like a link between quantum physics and so the uncertainty principle. So you have always a limit in your resolution as you have in imaging. And they are trying to find that limit, to reach that limit of resolution that can be achievable. And to do that, they proposed some new, let's say, mathematical tools, merging the Fisher information that can like allow you to describe the complexity of your system, and some operators that, let's say, we can think from quantum physics. And in particular, an Hermitian operator that is again something that wanted to describe these symmetries that we have in this mathematical description, let's say. And for example, here they try to tangle two situations where you have a scattering medium and you have something that you don't know, that is this theta, this angle, and you want to try to have the optimal estimation of that. And you can do this, for example, finding the best shaped wave that collide with this scattering material. And this is one of the approach that they proposed at the beginning, and they resolve this using this information, Fisher information description of what is in and what is out and the system. So you are trying to describe a process here that is something that actually you usually have in imaging, that you want to detect something and there is a probe that can be light, MRI field, something that collide with this system. So they formulated this new framework to answer to these questions that are really useful in, for example, imaging applications. And then they had another situation that they wanted to try to resolve, is when you have an object that is hidden by a medium and you have a camera. I will show you the image. So you have an observer, and let's say that this is your camera where you detect your image. This is something that a diffuser, so a material that is hiding an object, and you want to predict this phase shifting that you have due to this object. And they simulate different situations where you have, for example, an offset of this camera, what you will see from the camera, or if you have not a cross but a circle. So then what you will see. So this is the intensity. This is the Fisher information that this is this modeling of this image, let's say. And then you have this maximum information state that they applied to this data, and they see how this tool is responding in this situation. Here you can see that actually you can see from this image what was behind the diffuser, that is this cross. In this case, you have the most sensitivity in the middle of the cross. If you have this offset, it seems to be more uniform. They say because you have a different diffraction angle of light. Otherwise, if you have this circle, you have the most sensitivity just on one side of the circle. They say again that this is something that is expected. So because these methods are also have been applied, for example, in a semiconductor, in other field, in other field. So they are trying to translate this in imaging. So they expect something, they do not expect other aspects. So it seems that here, I know that when I saw this image, I said, yeah, you can't really see the cross maybe here, but you are seeing something that is hidden. So I was thinking maybe, let's say, because this can be applied to any kind of electromagnetic fields. For example, do you think like in echo imaging, let's say if you have like a sonar probe, an acoustic probe that what maybe you can with this modeling you can see something that is hidden, so in a layer in more depth. So there can be some application of this, I think. And then here there was another example where when they show that this maximum information state can predict this shift, this phi shift, in a better way that you just think which is the best plane wave that we can have in this scattering. So here you have like a more peak distribution of your most probable value. Here it's a little bit more messy. so yes, in this article, they basically try to prove and translate to imaging these new operators that you can borrow, let's say, from quantum physics, or they say that were applied in biomedical optics. So they're trying to translate these in imaging, and I really like it because it's a new way of thinking that at this stage maybe can seems like okay, a new method, something new, but maybe like if they pursue this research, maybe they can we can have new informations from an image that we already acquired, or have some more information about how to acquire in the best way this information. And yes, there was like one sentence that I always loved, that was from this board, that we are suspended on language. So what we see is actually the model that we are applying. And of course, every measure has a limit, but if we have to reach that limit. And I really like this article because they also explain here in the introduction this concept. And so I know this is really physical, but applied to the imaging field, but maybe a little bit far from MRI, but other imaging maybe closer. So that was it. I don't know if you have any questions.
Thank you, Leah. So I know you were super excited about this. Just to recap briefly, so there's a potential that we could push the boundary of resolution in MRI. Did I get this right?
No, MRI is a little bit far. Here they are talking about light fields, but can be like electromagnetic waves, of different lengths. So can be like with the visual field, or also they say in the discussion that can be translated to ultrasound or acoustic wavelengths. So maybe MRI we are a little bit far, but they don't talk about MRI, no.
Okay, but it could find its application in imaging the brain one way or another.
Yeah.
Okay. Any questions?
Hi, Leah. Thanks for presenting this.
Hi.
I'm just wondering, could you probably explain what, like, there are several differences, obviously, between MRI acquisition and other or biomedical optics, right? So could you explain what hinders the application of this method for MRI? So is it like an hardware issue? Is it the difference in the outcome measure that we're actually having, or?
The way I thought the link with MRI, but I say again that it's maybe the farthest application of this, because in MRI we have a lot of things going on when you for the like, let's say, the association of the signal with the position. So there are a lot of things there. So maybe with MRI, it's something that in the really raw processing, I was thinking about the Fourier transformation. Maybe you can apply there some filters that can try to just select these maximum information states. So it's something really at the beginning of all the process that we're gonna have then for the MRI imaging. So I see maybe there an application of that. So a kind of way like or like a filter at the beginning where you have the signal, the wave that you acquired, and maybe you can try with it's a kind of a filter to select which is the maximum information state, and then process there in the MRI pipeline. I saw maybe there an application, but it's an imagination. They are not saying that in this article.
So it's not used, or the idea is not to use it on basically spatial informed data, or?
No, it's related to spatial informed data, because one of the point of the article is that they could view, let's see, something that was hidden by a diffuser material. It say this here, and they just are proposing here a framework. So they just developed these mathematical tools, and they try to use these tools in the situation that we have seen. And so it's something really like basic physics research. So the possibility are many, especially in the imaging applications, as they said. But it's something at the beginning. It's like they just proposed this new way of analyze waves, so here light, but any kind of fields. So it's let's say a new method that can have many applications. And I don't know if I did answer.
I think you did answer pretty well, thanks.
Okay.
Leah, just a quick question. Coming back to the nice figure they have in the paper with the cross and the circle. I didn't, the next one with the hidden layer.
Here.
Yes, that one. So I didn't quite understand why we can more or less see the circle and the cross and are sensitive to it, but the circle I don't really see. Didn't get that part.
Yeah, it's also but yes, I was also like really excited at the beginning when I read the article, and then yeah, this is the result for the circle. So maybe here you have some pixels that are more sensitive, and they said that is normal to have I don't know why, but it's normal to have like this maximal information on one side. They say has the mirror symmetry in the system is broken by the diffuser. Again, symmetries. So they said that something that they expect that you can see simultaneously both edges. Maybe it's, I don't know, maybe it's because when you have like a phase shift, sometimes there is an interference of this phase shift. Like we have, you know, when you acquire an MRI, you can have like a flip if your field is too, because we are talking about waves. So maybe if you have a shift that is the same, is expected to flip on one side. Right. This is my explanation on the fly, but maybe that could be like this, because here we have like a symmetry and we are talking about waves, so maybe there is something like that.
Thank you. Glad I'm not the only one who was puzzled by this one. Right, we're on the dot. This is all we have time for this week. Thank you so much for bringing those interesting papers. Thank you so much for discussions. Very physics heavy this morning, but I hope you have an exciting week, and I can't talk today. I hope you have an exciting week in science. And we see you next Monday, 9:30 with your new papers. Thank you so much for coming.
Thank you.
Bye.
See you. Bye.
Thank you.
Thank you.